Hello everyone, welcome to the next lecture of op-amps. So we are talking about the applications of the non-inverting configurations of an op-amp, and today we are going to discuss a difference amplifier. Okay, so let's start with that. Difference amplifier. So what does a difference amplifier do? It takes a differential difference of the signals at op-amps inputs, right? So difference amplifier is going to take a difference of the signals at the op-amp inputs. If you remember, we said that, so if we're going to have these two inputs applied, V0, our V0 is a V2 minus V1. Our regular op-amp is a difference amplifier. It takes the difference of the two inputs and then multiply it with a gain A. So the question is, why can't we use op-amp directly as a difference amplifier? So can we use this configuration as a difference amplifier? And the answer is no. And why not? Because of A, right? A is ideally infinite, otherwise extremely large. Right? So our output will be saturated, right? Our output cannot be infinitely large. It will be saturated, slightly lower than the power supply's input. So that is why we will not get the difference and or the amplification, but always a saturation. So what do we want is, we want a stable, predictable, and finite gain. Right? So we want to design an amplifier, a difference amplifier, that will take the difference of the two input signals applied at the inputs, and then it will provide us a finite gain and a predictable gain and a stable gain. Another feature that we want in this difference amplifier is, we want it to reject the common mode signal. For example, interference present between two input signals. Right? This is commonly known as common mode rejection. Sorry. All right, so these are the basic features of a difference amplifier. Here's our regular amplifier, which is a difference amplifier. We cannot use it directly because of the infinitely large open loop gain. Our output will always be saturated, and we want a finite and a predictable gain and a stable values. So that is why we have to design a difference amplifier. An important feature of a difference amplifier is it should do the common mode rejection. We touched upon this topic earlier as well in this chapter, that whatever the common signal that is present in between the two inputs, it should be rejected in the in that amplifier configuration. Okay, so here's the circuit diagram. So this is how the difference amplifier will look like: negative, positive, V1, V2 R1 R2 R3 R4 V0. Right, and let's call this node voltage as V positive, and let's call this node voltage as V negative. All right, and the current that is flowing here is I1 and here I2. All right. Right, so assume ideal op amp. With A equals infinite, A V positive minus V negative. Now since A is infinite, this means that our V positive should be equals to V negative. All right, now let's solve this circuit now. So let's look at the V negative node here. All right, so at a V negative node, if I'm going to apply the Kirchhoff's laws, I2 R2 plus V naught so V naught should be equals to V negative minus I2 R2. And we know that this is an ideal op amp. And I positive equals I negative equals 0. So I2 must be equals to I1. All right, so what is the value of I2? Let's find the value of I2 here. I2 equals to, so if we're going to solve for this branch or this loop, I2 equals to V let's solve for I1, and I1 is equals to I2. I1, okay, so let's solve for this one, I1. So I1 would be equals to V1 minus V negative over R1, and that should also be equals to I2. Now we can replace this value over here. And the value of our V naught will becomes equals to V negative minus I2 minus I2 is V1 minus V negative over R1 into R2. So this will be equals to V negative minus V1 R2 over R1 plus V negative R2 over R1. Excuse me, sorry about this. All right. Now what we can do is we can take the V negative common here. So our V naught equals, if we will take the V negative common, we're going to get 1 plus R2 over R1 minus V1 into R2 over R1. Let's call this equation 1. So this is the value of V naught as of now. Now let's apply a voltage divider rule at V positive. Apply a voltage divider at V positive. If I apply a voltage divider at V positive, I will get V positive equals V2 into R4 over R4 plus R3. And since V positive equals V negative, so I can replace this value in equation 1. Replace in equation 1. Okay, so let me put down this value on the next page. So my V naught will become right, so this, since this V negative is equals to V positive here, okay, due to this thing, so I'm going to replace this value now. So V naught will become V2 into R4 R3 plus R4 into 1 plus R2 over R1 minus V1 R2 over R1. So let's multiply these. V2 into R4 R3 plus R4 plus R4 R2 R1 into R3 plus R4 minus V1 R2 over R1. V2 okay, so I'm going to take a common R3 plus R4 into R3 plus R4 into R1. So R4 R1 R3 plus R4 plus R4 R2 R3 plus R4 minus V1 R2 over R1. So this thing will be cancelled out. So we are going to left with V2 into R4 R1 plus R4 R2 over R1 R3 plus R4 minus V1 R2 over R1. Okay, so if I will take out let's say in the numerator I am going to take out R1 and R4, so I am going to be left with 1 plus R4 R2 R1 R4 R1 R4. I'm going to take out this again. Alright, so if I will take out this one over here as well, the value that I will got is R3 over R4 plus 1 minus V1 R2 over R1. And this will be cancelled out, and this R4 will be cancelled out. So it will be V2 into 1 plus R2 over R1 over 1 plus R3 over R4 minus V1 R2 over R1 V naught. Alright, so here's the derivation of that circuit, and as you can see, this is our difference amplifier. right? Our output is the difference of the two input signals that are applied at the inputs of the op-amps. So, so let's analyze this thing a little more. So what we want to do now is we want to find a condition. I want to find a condition which cancels the common mode signal. Alright, so I'm interested in finding out the condition under which this difference amplifier will cancel the common mode signal that is present in between V1 and V2 and will only multiply the differential signal. Right? Okay, so for common mode cancellation, for common mode cancellation, V0 should be equals to 0, right? What we want is we want our output to be equals to 0 when V1 equals to V2 equals to V. So if my excuse me, right, so what do I want is I want my difference, my amplifier to only multiply the difference and any common signal that is present, it should be 0, it should be cancelled out. So for example, if my input signals are the same, then my output should be equals to 0. Right? So I'm going to apply this in equation A. So let's call this as equation A. Now my output will be 0 and both the V1 and V2 will be equals to capital V. So if I will put down these numbers, 0 equals to V into 1 plus R2 over R1 over 1 plus R3 over R4 minus V R2 over R1. So this shows 1 plus R2 over R1, 1 plus R3 over R4 equals R2 over R1. So multiply, cross multiply R1 into 1 plus R2 over R1 equals R2 into 1 plus R3 over R4. So R1, I'm multiplying these, plus R2 equals R2 plus R2 R3 over R4. So R1 equals R2 R3 over R4. Right, so from here we can see that R4 over R3 can be equals to R2 over R1. Alright, so this is the condition. Yeah, sorry about this cough. So this is a condition that is that can be used to make sure that our common mode signal in the difference amplifiers will be rejected. All right, so let's put that back in equation A. Our equation A was this. So if I will put this condition back in the equation A, my equation will become okay, so let me do that on the next page actually. V naught equals V2 into 1 plus R2 over R1 over 1 plus, initially it was R3 over R4, and now I know that R4 over R3 equals R2 over R1. So it will be R1 over R2 minus V1 R2 over R1. Right, it will be R1 plus R2 over R1, R2 plus R1 over R2. So this will be cancelled out, minus V1 R2 over R1. So V2 would be equals to R2 over R1 minus V1 R2 over R1. Interestingly, once you apply this condition, we can easily see that our V naught equals R2 over R1 into V2 minus V1. So here's the difference amplifier. Where and this represents our differential gain here. Differential gain AD, which is R2 over R1. Right, so this is the difference amplifier with a gain of R2 over R1. All right, there's one more concept that we want to discuss here in this difference amplifier topic. And that is input resistance of differential amplifier. All right, so let me redraw the difference amplifier again. Negative, positive. We had two resistors here, and one more resistor was here. One resistor was in the feedback. V1, V2, R1, R2, and we saw that for CM common mode rejection, what did we see? Our condition was R2 over R1 should be equals to R3 over R4. Oh, sorry, R4 over R3. Let me confirm that. Yes, R2 over R1 equals R4 over R3. Alright, so from here we can see that if we want the common mode to be rejected, common mode signal, then I can make my R2 resistor equal to R4 and my R1 equals to R3. So R1 here, R2 here, this was originally R3. Now it can also be R1 and this can be R2. This will make sure that my common mode signal will be rejected. All right. So there's one more important consideration here. And the consideration is for gain to be higher. We saw that here, R2 over R1, V2 minus V1, right? Our V0 was R2 over R1 into V2 minus V1. So for gain to be higher, my R1 needs to be smaller. And since R1 equals to the input resistance of the differential amplifier, and we know that to avoid signal loss, our Rn should be higher. So this is the drawback that we run into, that in order to have a higher gain, we want our resistance to be smaller, but in order to prevent the signal loss, we want the resistance to be larger. Now we will see in the next lecture, we are going to see how we can use an instrumentation amplifier, another application, to achieve the same thing. So we can solve this drawback by developing an instrumentation amplifier that we are going to talk about in the next lecture. All right, so with that, thank you so much. I will talk with you in the next lecture. Thank you. Bye-bye.